I haven't done in this room before, but now I should be streaming. So in case you want to go back and see something later, in the welcome page in Insight, you can see the link to where this is going. And there's also a link to where you can see them afterwards. I will, at some point when I remember, or you remind me, I will rename the different clips so that you can actually make somewhat sense as to when was this recorded, so you can find your way through it. But I experienced previously when I did not stream this course that there's always some questions that I remember you said this, but I just did not quite recall what you said. I don't know, I mean, how many of us have had that experience before? I mean, count me in as well. So welcome to Applied Statistics, statistical software. I also had to go and get my own microphone because the one down here, that's an error on those. Both of them actually, so, but that is a minor problem. We are quite many this year. There's also a few have not arrived today because of traveling and other things. I heard from a few of you, and there's maybe more who did not care to inform me. That's perfectly fine. But it means that we will be probably quite busy. So the outline for today, or maybe mostly this morning, is to give you a brief overview of what we're going to do, what the content is. I assume that you all know R. Anyone who does not know R at all? Some. I think we'll make a small separate session for you guys in order not to bore everyone. That because you can say, as I've listed the Introduction to Statistics course as prerequisite, then I will kind of, and that course is using R, then I'm assuming that you're somewhat familiar with things. So when we go for the first exercise session, let's just gather down here at the front, and then we'll make a small session there. I think that's the best way to get about that. So the first week basically is going to be some fairly short lectures. Most of the time is going to spend on hands-on exercises. And then Friday afternoon, at some point, I will introduce you to the first case study, which is, you can say, the purpose for the second and third week. Saying that you will have two different projects, one starting on Friday and one starting in the middle of next week. And then the last 2 days will be an all exam. And if you want more details, then I have the, let me just go back here. The course website has a program where you can see all the topics. I know it's a bit small right now, for the various days during the first week here. And then you can see for the second and third week, here are all the time points and deadlines and things to be aware of when we get there. I will repeat that, but now you know where you can find it. Given the number that you are, I have moved the deadline for handing in the last to Tuesday evening so that I have time to read. Then I have a little bit more than 24 hours to read everything you've done. And then Thursday and Friday will be just full throttle presentations. It's usually quite nice. And the way I run it, I want to just tell you right now, is a little bit different in the sense that you will be working in groups of preferably 3 students each group. We'll get back to that. And then each group will be acting as consultants for another group, which means that each group will hand over their report to another group. I will take care of that. And then that other group will read it. And after a short presentation of what you have done, the other group will ask you some questions. I may add in some questions as well. Then to comply with formalities, I also have to ask individual questions. But I'll do that at the end. But I think it's quite good for you to learn and have to reflect on what other people did. And then you are going to come there and ask questions to get things explained that they did different, or maybe they did something wrong, or maybe they did something that was even better than what you did, or just something different in a good way where you did something different in another good way. And I always get a question, but what if we can't ask any questions? But on the day, I've never experienced that anyone who actually read the other report could not ask any meaningful questions. It's not a big problem. I mean, even if you read your own again, you can probably ask yourself some questions that you would like to answer, or to have an answer to at least. So that's, you can say, the way we do it here. We'll have 40 minutes for each of these sessions. So it's going to be a little bit packed. You have 10 minutes to present, 10 minutes for discussion, and then 15 minutes for individual questions, leaving 5 minutes to change. And then it's going to be a busy day, but usually it works out to be a good day. 2 days. But it also means that you don't have to be there all the time. You only have to be there when you're presenting and when you are the company asking questions. And I will do it in a way so that you're coming in blocks, so you're not presenting for those who are also asking questions for you. I make rotations so that it's always, you can say, a new pair, so that there won't be any kind of whatever thing you could figure out could happen in case students felt bad or something about someone else. So I make rotation so it's within, say, a 3-hour slot that you will be both presenting and asking. That usually works out. And the planning of that's in a long time from now. So what we'll do this week is that, as said, I will give a short lecture. Most of the time will be spent on exercises, but also to prepare yourself to kind of present what you've done. I don't know, most of you are probably experienced in just handing in reports, doing written exams, or even doing oral exams, but it's different when you have, you can say, more time to present what you've done. And when talking about statistics, a large focus in this course is actually how do you present what you did. It's not just about doing the right thing, but it's also about making sure that the receiver actually understands what you did and the reasoning for doing what you did. So a large part of this is also about presenting. So in order to practice for the exam, what I will request that you do, and hopefully we can get around to all of you, hopefully you'll be working in groups, and I will give you an example of how this can be done when I present the first one, but all the exercises that you're working with, I want you guys to present that to the rest of you. So each morning we will start with that. Hopefully it won't take too long, but it always takes some time. I will show one just to show you what I expect. I don't expect a lot, but I expect that you present what you did. And for some of you, it's maybe not so nice to stand up in front of so many people. I will promise I won't stream that. And if you're good at doing things, I may also share some sample solutions to those later on. But I want you to be first on the scene. As said, we will need to be 3 students in each group, at least if everyone signs up. And there'll be 2 cases to work with. And the way it's done, you can also see that in the timeline, is that you'll hand in the first case on Wednesday, then I'll go home. Well, actually, I will give you an introduction to the second case Wednesday next week, and then I'll go home and read. And when I'm done reading, I'll come back here and give you some feedback. Both, I will give some written feedback to every group, and then if there is some general comments, I will give them either just as a message or as a discussion. So it's only the second one that's going to be part of the oral exam, but the first one will also be part of the grade. And I always get the question, well, how is the weighting of the report versus the oral presentation? And I don't know how many times you've done a similar thing. Basically, when you write something and you stand up and present it, do you expect those levels to be? No, typically you expect it to be at the same level. So what I typically say is that what I expect is that you present what you've done and you answer questions at the same level. So the oral part is a matter of tuning the grade. It's not where you can set the grade as such. The grade is set by the reports, but you can tune, in particular also within group, if there's someone who's the genius and the other one are not so much. I mean, I like to be able to give credit to that, but of course that person had to stand out sufficiently. And there's also, of course, the reverse of that, but hopefully that's not the case. I'll show you the course homepage. It's there. I updated it just before New Year's. It contains all the data that are going to be used for the exercises during the first weeks. Actually, the slides are not updated there. I will update the slides. I should have removed that line. I'll put the slides in Insight, along with the different files that go with that. There's also some links and material from R. Part of that is probably a little bit outdated, but I expect that all of you will be using RStudio, and we'll get back to that. That's a fairly easy interface to work with. You can also just run R as a standalone software, but then you don't have the integration as well, at least. There's also a few downsides of using RStudio. Maybe I'll get to say them, maybe I won't. I will use Insight for, you can say, messages that are formal, in the sense that it's about the exam, it's about things, for file sharing, but then I'll use Piazza for, you can say, all these questions and answers that comes along the way, in particular, given the number of students that we are here. Then, by experience, many of you will have the same question. So that's also one of the reasons for using Piazza. Some of you may also have the answers to those questions. So please answer each other's questions. If you don't feel like posting your name, you can be anonymous. I hope that can kind of help you all further, because I think ultimately, what is the most important thing about this course? From my point of view, actually, a general thing about statistics courses. Maybe I shouldn't say this in this way, but I don't care if the only thing you're able to do is a two-sample t-test. As long as you know that's the only thing you can do. The most dangerous thing is someone is doing statistics without knowing what they're doing. So you make conclusions based on things that have no reasoning behind. Everyone can fit a linear regression model. Not everyone can see if the assumptions are fulfilled to a degree so that you can actually trust the results. And I'll try to jump into some pitfalls on purpose and see what happens from there. But I think that's the most important thing. And we can all learn more methods. But the challenge is to learn to know, is what I'm doing actually appropriate, or should I do something different? Should I call for help? Call a friend or whatever. I think that's the most important thing. After that, of course, the more methods you have in your toolbox, the more problems you can solve. Not to be but the first thing is what I'm doing adequate or not? And sometimes assumptions may not be fulfilled, and you know they're not fulfilled. But it may still be appropriate to do what you're doing because you have some statistical rules, law of large numbers and stuff like that, that helps you out in a sense that, well, it doesn't matter that things are not totally normally distributed as long as it's sufficiently close. Say, a t-test is actually quite robust to small deviations from normality if you just have enough samples. So there's a lot of these things where small departures doesn't matter too much, but too large departures, everything starts to kind of be wiggly at some point. And navigating there, it's a gray zone. And that being clear about, is this something that you can just trust, or is this something that is a little bit more on the loose side, or should you just totally neglect this result? Having a communication of your level of trust in what you're doing is important. We'll get back to, of course, how you can improve the trust, but that's another thing. Regarding Piazza, I don't know how many of you have been TAs in other courses. I mean, I have. What is the most important learning from being a TA?
To communicate things before everyone asks, or like to everyone, and not say the same thing individually to 30 people.
That's one good thing, but what is the learning? That's one learning, of course. I was thinking of something different. I totally agree with what you're saying. Another important thing is also, by helping others, you also get to learn things yourself, because you have to know it at a higher level in order to communicate it. So that also means if you can answer other people's questions here, you will also get some credit from that in your own learning. So, what we'll talk about, descriptive statistics. I think most of you should have done some of that, at least. Comparing treatment means. You've all done Ttest. Not so many of you have done non-parametric tests, at least as far as I know. Proportions and counts. That's what we'll do today. Since it's a 4-day week this week, I have kind of changed the program a little bit compared to what I usually do, and taking the proportion count and move that to today. That also means that the number of exercises for today is a bit higher than for the other days. I don't expect that you get through all of that, but I will get to that later. Tomorrow we'll talk more about regression. I expect that you've all seen some of that, but we'll discuss some more further details on that, but also just, you can say, a quick recap of what should you know already. Just to get the experience for those of you who have done it for the last couple of, say, weeks, months, years. Analysis of variance on Thursday, and then you can say putting pretty much everything together on Friday. And basically everything between, everything post today until Friday is just warming up to the models on Friday, where we'll combine everything. And that's the foundation that we'll use. So, statistical procedures. As I mentioned, descriptive statistics, we've all done that. But do we all recall what it means? What is the descriptive statistics?
Is that the one you see in sport?
Sorry?
Football, when they try to lose too much time at the goal and they too much, so there's no analysis behind it.
There's no analysis, exactly. You're just displaying results, doing some summary, but you don't have any statistical modeling. So you have a presentation and display of your data somehow. So exactly, it could be, as you say, if you see a sports game, you see how is the possession of the ball and blah, blah, blah. Different measures. Yes?
Descriptive statistics is also used to being able to understand your data. How is it behaving?
Yes. That's part of what I mean by presenting. Okay. But yes, it is a matter of describing what do you have, in a sense, so that we have some variables. What do they actually mean? Are there anything that looks odd or whatever? What is the scale? Any considerations that you should have already regarding transformations? We'll get back to that in a moment. I just want to have the contrast between descriptive statistics and inferential. Because that's when you start doing, as you said, the borderline is you collect the data, but you start to draw conclusions based on hopefully appropriate statistical models. And but the descriptive part is just presenting your data. And it's important to always look at your data before doing things with it. I mean, when you are a Dane and you import data that comes from, say, the US, and you have dates where you have the month, then the day, and then the year as the date format. I can see someone smiling, have tried that before. Stuff like that is just annoying if you don't get it right. Because computers tend to try to help you. Sometimes their attempt at helping you actually doesn't help too much. You're fooled by the fact that it encodes things in a different way, and it looks like dates, but it isn't. Stuff like that happens. So it's a matter of also checking that what you got in was what you expected to get in. So I think we all know this. When we have analysis of data, what is then data? Basically, what we talk about observations. Yeah, we're familiar with that word. But we also talk about how many variables do we observe. So just to have this distinction between observations, each, at least in this course, we'll assume that observations are independent. So you have particular individuals in this case where you measured 4 different variables. And then you can continue adding new observations for new individuals. Typically, each sample of some kind will be an observation, and then you measure some variables for each of those. And you can, of course, record things in different ways. You can measure something, or you can count, or you can sort, or whatever you are doing. That depends on the case. And sometimes you go out and collect data, and sometimes you are in a fortunate situation that you can actually control an experiment. And you design the experiment, and you get the data from that. To get the most out of that, there's a course in design of experiment. I won't cover that in detail, but just say that sometimes you're lucky, and sometimes you have to live with what you get. And of course, if you want to analyze stuff, you should use something that is meant to be used for that. So, as I said earlier on, I do recommend to use RStudio. Here's a link if you do not install it already. I like it because it runs pretty much the same way on all platforms. I mean, the only difference is if you have a Mac, then you need to press a different key than the control to do things. But that's kind of the usual keys that you use. It also means that I can go around and help you all easily. Except if you have a French keyboard. Those are the most annoying ones. So I'm trying to learn, but I'm not good on French. Or Arabic, but that's another story. So I recommend this book, but I don't expect that you all buy it. You can also find it in findit.dtu.dk. What I like about this book is that when you just read it, it's, maybe that's paraphrasing a little bit too much, it's like taking a novel. You can take it and read it, and you just walk along the story. So you get kind of a nice introduction to things, and it actually covers quite a bit of ground. Actually, it covers more than what I will cover in this course, because it covers some of the extensions to models that do not assume normality, where you cannot do sufficiently with transformations. It doesn't go in full depth everywhere, but it goes in sufficient depth and sufficient detail in many places. So I remember when I first time read it, and I was like, okay, there was actually something you could just read. It was not like you have to think every 5 lines what was meant. It's in a very nice language. So usually I start out with a small introduction to R script, just walk through. But for most of you, that will be too slow. So that's what I will do, covering how to do some basic things. I'll do that, you can say, for those few who needs that, rather than to do that for everyone. Rather, I will get back to, you can say, the basics and start there, because it's always nice to start with something that we can handle. So a common problem is that you have two different treatments, two different groups, and you want to say, are they different? Yes or no? And the typical approach is to do a t-test to compare one or two. One, if you have a reference value that you want to compare, is this group different from the reference? Yes or no? Or two, if you have two groups and you want to see, are they actually different? Yes or no? And the assumption is that each group may have the same or different mean values. The null hypothesis is that they have the same mean value, and the alternative hypothesis is that it's different. This is the so-called two-sided test. I don't know how many of you know what the difference is between a two-sided and a one-sided test.
It lies in the alternative hypothesis. If it's only one-sided, then you only assume that mean will either be like higher or lower than what you're comparing it to.
Yes. So if you have a density function for a normal distribution, and let's just say we want to compare this. Let's just make a one sample t-test. This is the sample mean value, and then we have a normal distribution. If you're doing a two-sided test, then you're looking at, you can say, having equal proportion of probability in both tails. If you're only doing a one-sided test, then you're only caring about either the higher or the lower tail. It makes a lot of sense when you say it, but it's always a little bit more difficult when you start doing it. And what we'll do is to use the so-called the p-values as a selection criteria. And if you don't specify anything else throughout this course, we'll use a 5% level for significance everywhere. And that's kind of within most engineering disciplines, that's fairly okay. If you're within medicine and other areas, you may have more strict levels, so you have to say, show something is even more significant than that. But for now, let's go for a 5% level. Do you actually know what that means? Have you thought of what that means? Someone else, thank you. Yes?
Something to do with how likely the sample or the sample values are to be more extreme than what we assumed.
Yes. Under the null hypothesis. Under the null hypothesis. So if you have this up here, then if you have some observations and you have the distribution for the mean value here, then you can say the question is, if you just do the mean value of a number of, say, 10 random normals, the mean value, even though they're standardized, the mean value is not going to be 0 for each of those. You will have the distribution of those. And then it's looking at that distribution, how extreme is the one that you observed compared to that distribution. So how large a fraction of samples under the null hypothesis will actually be more extreme than what you observed. So that means that we will see, and I'll, some point in time, not today, I will play around with those just to show you things that you did not always consider. But there's one thing here, and I think from a statistical point of view, being a statistician, you never do one thing. You either reject the null hypothesis or you fail to reject it. Some may use another word instead of fail to reject and say they accept it. From a statistical point of view, that's not correct. I know I may also end up saying it. It's not that. But I tend not to do it because it's not adequate. And what is the reason? I'll discuss that later. So when you do a t-test, you assume that things are normally distributed. And a t-test, as said, if you have enough samples, it's fairly robust to smaller departures. But that's the assumption. And how do you check it? Well, the typical thing is to start doing some graphical things, say a QQ plot. I actually prefer that much over a histogram. But, I mean, histograms are also nice to look at, and they're easier to explain. But on the other hand, histograms are not that informative, because where you make the breaks kind of matters a lot toward what you actually observe. You can also do formal tests for that, but this is where you should be remembering that some of these tests, if you have a large sample, they are very sensitive to things being non-normal. So if you have a small departure from normality, it really doesn't change the test that much. It may mean that the 5% level is not exact a 5% test level, but it's still a good approximation. So whenever you have departures from normality, all p-values becomes approximations. But, I mean, we've all lived with many approximations. Some are good, some are bad. And that's where the gray zone come in. So, a first example, 2 mean values. A very old biology lecture, Herman Bumpus, looking at, you can say, natural selection. Is there anything to it, or is it just a good old story? So he took some house sparrows that were brought to Brown University after a severe winter storm, and then some of those birds, they survived, and some died. And then the question is, could that actually be explained by natural selection? So what he did was to, or someone did, was to measure the humerus, which is kind of the arm bone in the wing, for 24 adult male sparrows that perished and 35 that survived this winter storm. And now the question is, what is the appropriate thing? The question is, are these humerus lengths different for survivors relative to those that perished? And if so, how large is that difference? That's an easy question, and the appropriate thing to do is, you can say, of course, a t-test in this case. But first, I'll just read the data, and as a first just look at data, I tend to always do a summary of the data. But I tend to also often do one more thing. But the summary, just to say what we have. We have 2 variables in this data set. The first one is humerus. That looks like a measure of some numbers. That's probably meaningful. And then there's a code here where there's some 1s and some 2s. Most of them are 2s. So what does that mean? What are they coding for?
It's kind of a binary code to indicate whether it died or not.
Yes. And the way to figure out which one is coding for what is to say that we have 35 that survived and 24 that did not survive. So that means that we have more that survived. So the median here is coding for those that survived. So 2 is for surviving, 1 is for dying. A string representation is just to show what is the, and I think that's, at least in practice, the coding here is an integer. That is what often helps you figure out what was wrong when you try to import the data. And here you can see, okay, you just have ones. So that's all fine. This here is just to say I want multiple columns. I mean multiple frames, and I want 2 rows and 1 column. And then I'll just do the histogram. And with the zoom level, it doesn't look too nice. I could make it nicer by adding a text. So this was code 1. So this was died. And if you just look at the histograms, like here, it's very difficult to say anything about normality, right? Because you don't have that many samples. If we just plot everything, you can just see that they're just ordered. Here I'm just plotting them in the order they are in the dataset. So first we have those that died, and then we have the red ones are those that survived, because I used the color as my code. So it's quite difficult, but let's look at if you do a QQ plot, there's a function called QQ norm, and then adding a line to it. When you just look at it, the question is always, is this sufficiently close to be normal? Yes or no? When I look at this, it's not too bad. You can argue that maybe the lower tail here sticks out a little bit too much, but I would make that a comment and say it's not too bad, given the number of samples that we have here. I don't know why R did not combine these two into one command, but often you just want that to be one command, because you always don't want to just have that, you want to have something to compare it with. So what I tend to do is either this, to make my own, the QQ function, just defining a function that takes some numbers and does the QQ norm and then the QQ line of that. And then I can run it like this. And then, so that was code 1, and that is code 2. Now, an alternative, which I actually kind of like, is from the car library that adds a confidence interval to the QQ plot. So where does that confidence interval come from? It comes from the fact that if you have a distribution of this and you get a number of samples, in this case 24, which if one of them and 35 for the other one, then when you sort them, and that's basically what you do when you do a QQ plot. You sort the observations out here, and then you plot them as function of the corresponding quantiles here. And there's a way to figure out how to kind of where to start. So you don't have the minus infinity and infinity values out there. I won't get into those details, but when you sort them, you do what is called order statistics. I don't know how many of you have done that. How many took the introduction to probability theory course? Not that many. But the easy way to kind of envision an order statistic is to look at, say, the maximum of two numbers. What is the distribution for that? If you have two die and roll them, what is the maximum of that? So that's what you do. You look at the ranked statistics, and then you look at what is the variance of at that level of standard deviation, and then you plot that to show you. And this is a 95% interval. So you should expect 95% of your observations to be inside here. And this is where, okay, there's 1 point out in the tail for this one that is outside. That's probably okay, right? For the other one, they are all inside. So this departure, as we looked at just before, from normality at the lower tail, is not too large. It's there, but it's not significant. So that means that it's okay to actually go about and do the t-test regarding the assumption for normality. But there's one more thing to test. The variances should also be equal. So what I'll do now is I will split the data. So I have those that perished and those that survived. And then I will index those and say, what is the variance in those two compared to one another? The ratio of variances is 1.4. So the variance in one group is 40% larger than in the other group. But the 95% confidence interval for the ratio includes 1. So that means with 95%, we cannot reject that they have the same variance, even though that the observed difference is 40%. We can also give them some names, so they're not just 1 and 2. Now they are rest in peace and kicking, or kicking, and do the same thing. What I like to do rather than histograms is also looking at the empirical cumulative distribution function. So this is for the one sample, and then if you add the other one on top of them, it's fairly easy to see, when you look at the distribution of the two, what do you expect? Are the means different? At least all the red curve is to the right of the black one. So it's not unlikely that there is something to come for. But now we tested normality and we tested the variance homogeneity. So now we'll do the t-test to compare the two. And we get a p-value of 9%. So what is the conclusion? Yes?
There's little evidence saying that there maybe is no difference between the mean values.
Yeah, there's not sufficient evidence to prove a significant difference. So we fail to reject the null hypothesis. Now, but what was the question? Was this actually the appropriate analysis that I did? The answer is no, I did not make the appropriate analysis. What did I do wrong? I mean, it's not wrong what I did, but I did not actually answer the question. What was the question? The question was natural selection. So what is kind of implicitly there in that formulation when doing a t-test? What did I do here? I made the alternative hypothesis to be true difference in means is not equal to 0. Is that actually the appropriate analysis?
But isn't it one way to say that if it isn't 0, then there is like a natural, I mean, the natural selection wins over
Yeah, but you could also argue that what you're testing here is the two-sided alternative. That means you're also having you're looking at the probability of having those that survived being smaller. You're also looking at those being significantly smaller than those that died. But when you ask for natural selection, implicitly you're also saying that those that are bigger and stronger, you want to test if they are greater than. So you want to have the alternative not to be both. Let me just... So the alternative here can be either two-sided, which is the default, or greater or less. And it will automatically match, so you just need to write sufficient number of letters to make a unique match to either two-sided, greater or less. So a G is sufficient. Now, how many of you can answer what the p-value is going to be when I run that line? It's a very easy answer. How do I find the answer? You don't have to give me the numerical value, but what is the solution for the answer? Yes?
I think you just divide your result by 2.
Exactly. You just take the p-value from before, the 9%, and divide by 2. So that means when I do the alternative, and I would say regarding the question that you started off with, appropriate analysis, you're actually able to say that the p-value becomes less than 5%, which means that there is a significant difference, proven by this fairly small sample. But the important thing here is that you have to formulate your hypothesis before you start doing the analysis, before you start looking at the p-values. Because if you just looked at the first p-value, say that's 9%, I know that if I just divide that by 2, I can prove significance, so I just have to ask the right question. Then you are on the list of, there are three kinds of lies. Lies, damn lies, and statistics. Side box. So always formulate your hypothesis before looking at p-values. And then you can start doing things. Later on, we'll get to kind of operationalize some of these things, and we just start testing and testing. And we are not always so clear on what is the initial hypothesis. But it's important to be mentally aware of that. Now, we discussed departure from normality, and one alternative, if things are not normal, there are basically 2 different things you can do. One is you can try to make a transformation so things becomes more normal, and the other is that you do another kind of test. But before discussing that, I think we should have a break and resume at 10 o'clock. Because I can just keep going, but I shouldn't.